Hello, this is Dr. Liu. In this video, I will show you what the dot product is. This is a vector dot product and also what we can do with it. So let's get started. Dot product. So basically, a dot product just involves two vectors. So let's assume there are vector A and B. And to perform a dot product, we put a center dot here. So that's a dot product. And this product produces a resultant scalar. So if you think about in terms of input and outputs, we had a scalar multiplied with a vector. So the input would be a scalar and a vector, and the output would be another vector, a scaled vector. And in this case, we have two inputs, a vector and another vector. And then we have an output, which is a scalar. It makes sense. We have different types of inputs and we want different types of outputs, so we can define different types of processes. And this process particularly is called a dot product. So what do we do with it? Is there anything we can do with, such as applying this to something? So here's one example that we normally do a lot, is to find angle. And we can find the angle between the vector A and vector B using the dot product. So let's write this down. So applications, find the angle between two vectors. And we can also find lengths of projection of one vector along the other vector. So lengths of projection of one vector along the other vector. Okay, so we'll demonstrate both. So now let's take a closer look at the definition here, A dot B. So what are we supposed to do with A dot B? So let's define this as scalar. A dot B is supposed to be A, this is magnitude of A, B times magnitude of B times cosine of the angle between AB, theta AB. All right. So if we draw this out, I can draw a diagram here. First quadrant. So randomly draw an A, and then draw a B, different lengths. So two vectors, XY coordinates, define the typical way. We also have an origin. So this is theta A, and this larger angle is theta B, and the angle in between is theta AB. Okay, so this is just a two-dimensional example. And in this example, you can find out the angle AB by just finding angle A, finding angle B. We know how to do that. We have the if we have the magnitude of angle, then we just subtract the two angles directly. If we have, instead of the magnitude angle, we have x and y components, we can convert them into magnitudes and angles, and then we take the two angles and subtract them. But that only works in 2D. What if it is in 3D? Just imagining you're in outer space, you're in one spacecraft, there's another spacecraft nearby traveling at a different direction. So what is the angle if you're traveling against that other spacecraft, right? So in 3D, it'll be not as easy as this. So we need a way to find the angle between two vectors. All right. So we already said that this AB dot product is A magnitude times B magnitude times the cosine of AB. And we need to find a way to actually represent this another way so that this will be an equation. One side involves an angle, the other side will involve something known such as component-wise expression. This is magnitude angle-wise expression, right? So there will be an equation that you can solve. So that equation is this way. I'll explain just in a little bit. A dot B. This is in the magnitude angle representation. We can also use the component ax bx plus ay by plus az bz. So why exactly is this the right format? Well, we'll explain this in a little. So we want to define something called unit vectors. So unit vectors are vectors with a unit length, such as 1 unit. So if you look at my diagram here, let's say that two blocks is a unit. So I have several units in the x and several units in the y. I'll mark them for your convenience. So what is a unit vector? X with a hat on top. So this vector magnitude is equal to 1. That's the unit, and it's still a vector, and the direction is positive x direction. So that makes it easy to understand. I'll use a different color, and the unit vector x hat is just this, right? One length and the direction in the positive x. So that is unit vector x hat. And you can also define unit vector y hat. I'm just making it really thick. So that's y hat. So there's also a y hat, magnitude also equal to 1. Direction is also positive but in y direction. And then z unit vector, magnitude is 1 and direction is positive z direction. So these three vectors are, well, they're mutually perpendicular to each other, right? They're also all the same length of 1. So let's think about the expression with unit vector involved as a and b. What is this? So let's see. Let's take x and dot with y, both unit vectors, and we're just following this expression, this definition. So we'll have x magnitude and y magnitude, both of which are 1. Cosine of angle, x and y directions, they're mutually perpendicular, so there's a 90-degree angle. Alright, cosine 90 is equal to 0. So that is a 0. Okay, so x dot y, direction y, is equal to 0. What about x hat dot dot itself? Well, we'll have x hat magnitude, so 1 times 1. These are not dots, because dot products, because there's no vectors involved. And then cosine of angle 0, because x is parallel to x, so the angle between the two is 0. So cosine 0 is actually equal to 1. So this result is equal to 1. Let's move that. Line this up. Okay, so we just had two calculations. X dot y is equal to 0, x dot x is equal to 1. So if you continue on with the calculation, you'll also conclude that y dot y, which is also parallel, right? And that's equal to 1. So is z dot z, because parallel things have 0 angle. And then perpendicular things will have 90-degree angle, so they all follow that. X dot y dot z, or z dot x. And it doesn't really matter the order, which one does which one, because both our magnitudes are here. This angle does not really tell you which one was the first operand in that dot product. So it doesn't really matter if you have y dot z or z dot y. They're the same thing. They're zeros. So now we have some rules of how to calculate a dot product for these unit vectors. So why do these help to get that expression understood? Okay, so let's go ahead and apply our unit vector and their dot products to this expression now. So A dot B. That is supposed to be AX, X hat, plus AY, Y hat, plus AZ, and Z hat. Okay, so this is just another way to express the same vector A, because A has that many units along the X, that many units along the Y, that many units along the Z, right? So then the dot is between the two vectors, BX, X hat, BY, Y hat, and BZ, Z direction, right? So that's that. And since we are talking about a product, you can do distribution rule, right, with product. So distribute this term dot this term. Well, first term dot first term, first term dot second term, first term dot third term. You can do that. There's going to be 9 dot products if you expand it, and hopefully we don't have to do that just to see the trend. So we're going to distribute, right? And I'll draw a few. Okay, I'll start with black. I'll distribute like this, and then I'll distribute again, and again. Okay, so distribute this term, and let's see what that is. So here AX, and here we have BX. So AX BX, X hat dot X hat. Okay, that is equal to a 1. Okay, so that's equal to 1. Alright, so let's see the next term here, red. So AX BY, AX BY, then X hat dot Y hat, X hat dot Y hat. So that's supposed to be equal to 0. Okay. And the next term, so AX BZ, and then X hat dot Z hat, X hat dot Z hat. So that's also supposed to be 0. As long as you don't have the same vector dot itself, you will have a 0, because these unit vectors are mutually perpendicular. The 90-degree cosine gives you 0. So that's only distributing one term, and then you distribute the next term, distribute the next term. The only things that are actually non-zero are distributing this term to the corresponding term that has the same unit vector. So you'll be dotting y with y. So it's easy. I'll just draw this, and the other two distributions are 0. And then I'll draw that, and also the other two distributions are 0, right? So this is a 0, that's a 0. So I'll just add 2 more terms from the second term distributed with only one non-zero, AYBY. And the third term distributed over only with the third term in the other parentheses. You get this non-zero thing here. So what we have left, this is equal to 1. This is equal to 1, right? So we have AX BX. X, this is X, looks like a Y. So AXBX, and here AYBY, here AZBZ. All the other terms, we can call them cross terms, are 0. So that proved this formula works. Okay, so now that we know this formula works, we'll do some examples. So I have a few values that I can use for examples. So let's start with this one here. Vector A is equal to 3, 2, 5. These are rather random values I picked. B is equal to -6, 1, and 7. Okay, so full 3D. And then I'll have another example with 2D, the third dimension being 0. Okay. So let's calculate the dot product A dot B. Okay, so A dot B. Okay, that'll be AX BX, right? Plus AYBY plus AZBZ. And the product is what? Is a scalar, just a number, is no longer a vector. So ax bx 3 times minus 6 ay by 2 times 1 az bz 5 times 7 minus 18 plus 1 plus 35. So we have 19. Okay, so minus 18. So if this you subtract a 20, this is 15, but this is 17. Then there's also 2, 19. So that is the dot product. Okay, so let's do another example. I'll do it on the right side. So A in this case is equal to 13, 6, and a 0. And B is equal to 6, 8, and 0. The reason I have these two both in 2D is I have a 2D vector simulator. I can just make up these vectors and look at their angles and read the angles of the simulator, subtract their angles. I can get the answer, the angle in between the two vectors. So I can later compare that with how to do it with using dot product. Okay, so let's do the dot product. A dot B, ax bx, ay by, then az bz. Don't really have to do that, zeros, right? So if you sum them together, 126. All right. So I was saying that there are these two typical applications: find the angle between the two vectors and also find length of projection. So how do we find the angles between these vectors? Well, how about we do the easy one first. This one here, we can use our vector simulator to find the answer and compare it to what we could do with dot product. Okay, so here we go. Here's the vector simulator. I already have these set up. So A is 13 and 6, and there's no z, so 0. And B is 6 and 8. So you can look at the angle. A has an angle of 24.8 degrees, and B has an angle of 53.1 degrees. So if you subtract the two, just pretend this were 25, and then you have 25, 28.1 degrees, 28.3 degrees. So that would be the difference displayed here. But have in mind, there's going to be some rounding errors. So 28.3 degrees according to the vector simulator. So let's move it out of the screen. So the angle AB in this case should be 28.3 degrees from vector sim. Okay, so we trust that. Although the angles are only down to 1 digit after decimal accuracy, so we trust that. Okay, so how do we get the angle? Well, let's take a look at the formulas on the top. So A dot B is equal to this, which involves the angle. So that's where we're actually getting the angle. A dot B is also equal to this. So if we equate the right-hand sides of these two different ways of getting dot product, then we have a relationship between the angle and the components and the magnitudes. So let's do that right here. So A dot B is equal to AB cosine AB. So AB cosine angle AB. That's also equal to AX BX plus AY BY plus AZ BZ. So if we divide out the magnitudes, we get cosine angle equals AX BX plus AY BY plus AZ BZ, then divided by AB's magnitude multiplied together. So once we have the cosine, we can just take the inverse cosine and get the angle. Okay, so since we already have the top portion, which is A dot B, this is the top portion, right? So we can substitute 126 in here, but we don't have the A or B's magnitudes either, right? So we have to get A and B's magnitude. So let's get A's magnitude, which is 13 squared plus 6 squared plus 0 squared, ignoring that. And B has magnitude 6 squared plus 8 squared plus 0 squared, ignoring that. This is actually the 3, 4, 5 right angle triangle, just twice as long. So this is 6, 8, 10. So B's magnitude is 10. A's magnitude would require some calculation. So let's see what we have here in terms of Python. Okay, so I'll bring Python over. Okay, so let's see. To get magnitude 13 and 6, so we'll do this. Okay, so that is 13 squared plus 6 squared, and then raised to the power 1/2. That's taking the square root. So we have 14.3. Okay. So we have 14.3. All right. So now we can get the cosine. So the cosine to the AB is just the top portion is the dot product, 126. The bottom is 14.3 times 10. So then we can calculate angle, which is arc cosine this whole fraction. So this is 126 over 143. Good thing the denominator is greater than the numerator, otherwise we won't really have an angle. Alright, so let's get Python and calculate this arc cosine 126 over 143. So okay, so this will give us the angle in radians. So that's in radians. We'll calculate the degree by multiply that with 57.3. This is a factor. This factor is 360 degrees divided by 2 pi. That gives you roughly 60 degrees, but it's 57.3. Okay, so 28.2 degrees. And we were calculating, we were actually eyeballing the angle from the vector simulator with 28.3, right? Let's bring that back. So just subtract the two angles, and now we get 28.2. I think we should be happy because that simulator has only one digit after decimal, and we were also keeping 3 digits, 3 sig figs altogether. So that in that regard, these two values are the same. So let's move that out of the way. And we'll do 28.2 degrees. So that is consistent with the vector simulation's outcome. All right, so let's do one more since we have another vector here on the left side. So let's get this thing done as well. So now we know the steps. First we calculate the dot product, get that, and then we calculate the magnitude separately. Then we form this fraction, dot product on top, magnitude on the bottom. So that is the cosine, and then we take the arc cosine to get the angle. Okay, so this is still doable if you use your vector simulator as a cheat, but that is not. You cannot use that with these third dimension quantities. So let's just do the this way. So we'll get A's magnitude and B's magnitude. So never square a negative, just in case I mistype it. Okay. So A and B's magnitude. I think I have Python already set up to calculate them. Bring that back. So as you can see, I already set up A and B. So the way to calculate AB magnitude is this way. So that's linear algorithm, they call it norm. So well, we'll use that. So that's the A's magnitude, and we can also do B's magnitude. Okay, so 616927. Okay, so now we can do cosine theta AB equals the dot product on the top, and then A's magnitude 6.16, B's magnitude 9.27. So the angle is arc cosine this fraction and let's see what we get. Python, bring that over. So dot product over 8th magnitude is 616, or B's magnitude 927. Okay, and then we'll just scale it from radians to degrees. So the angle is 70.6 degrees. So here 70.6 degrees. I would never be able to guess that if you look at these, right? So now we have another thing about the length of projection. What was that about? Well, if you look at this diagram here, let's say that A and B are two vectors, and I want to know how long the A vector is projecting into the B's direction. So I can extend this B here. Okay, and I want to do a projection of A. So this will be the A's projection along B, right? So I can say A along B, or you can even call that A's component along B, just like A's component along X is called AX, right? So how long is this? Well, this angle is already marked, the angle between AB, and A happens to be the hypotenuse in this right angle triangle. Here's 90 degrees. So this is the side that is adjacent. So that should be A times cosine of this. Where do we see that? Oh, A cosine of that. Oh, it's in the definition right there. So I'll write it out. So if I want the magnitude, how long that is, it's supposed to be A times cosine of the angle between AB. So you project it along the B direction. And this happens to be AB cosine AB divided by B. So this is AB cosine AB is A dot B divided by B. So you want A's projection along B, you do a dot product, you divide by B's magnitude. Oh, this is pretty readily available. Here we already have a 19, and we have B's magnitude 9.27. So the A's magnitude along B, well, that must be less than A's magnitude itself, right? Less than and this. Well, so let's see what it is. 19 over 9.27. Let's get Python to calculate. So 19 over 9.27. So the length of A along B is actually 2.05. So here we have 2.05. And you can also do a B's magnitude along A's direction. That does the same thing. Assuming B here, you can draw up a another perpendicular line, and this would be the B vector is a component. Strange, but that is what it is. And you'll actually do B times cosine of this angle, which is also part of that dot product. So to get B's projection, you can do B's projection along A is A dot B over A magnitude. See, the subscript appears as a magnitude in the denominator. It's just like, oh, that's a little lower than that. This is a little below that, right? So if you want to memorize by that way, that works too. So you can calculate that, and in our case of 19 over A's magnitude is 6.16. So let's calculate in Python. So we have 3.08. 3.08. Alright, so if you wish, you can also do the same thing over here and see if you get the answer you expect. Alright, thank you.